Hello, and here's our first video where we talk about taking the information that we've gathered about increasing and decreasing behavior, concave up, concave down behavior, local max and min, inflection points. We try to gather that all together and draw a reasonably careful graph of some functions. And so just want to point out for starters that there are a few other considerations that we need to make as we go through this process. The first is we need to settle on the domain of the function, and we want to remember that that's the set of valid x coordinates, the valid numbers for x that we can substitute in the function and get something out. One particular thing that we're interested in is we want to avoid 0 in denominators. That's actually not going to come into play in any of the examples that I'm working in these first couple of videos, but it will come into play in the last video that I'm going to be putting together for this. Another important thing that we can do to sort of anchor the graphs, our graph sum, is to think about intercepts. That is, is the function intersecting our coordinate axes? To find a y-intercept, we want to remember that this is the value of the function, at 0. And to find x-intercepts, we want to solve f of x equal to 0. So we'll set our functional value equal to 0 and solve for those coordinates. So that'll tell me where the graph intersects the y-axis. And where it intersects the x-axis. Then another thing that we want to do is we want to think about asymptotes of a function. And so we want to go back and think about vertical asymptotes. I misspelled vertical here. Vertical asymptotes are going to occur when we get a positive or negative infinity out of a limit, one-sided limit, as we approach holes in the domain of our function. And then for horizontal asymptotes, we want to think about we want to look at the limit as x goes to infinity of a function. And if we get a finite number out from that limit, then you want to recall that y equals L, where L is that limit, is a horizontal asymptote. But we are going to be interested in just in general with end behavior here. And so we're asking, even if the function is going toward plus infinity or minus infinity, as we go off to the left or right of the graph, we're going to be interested in using that information to help us graph our function. Then we want to talk about, we've done a lot of work on finding local max and min values. We've got that information, so we may as well plot these functions and see what we've got. And then the other big thing, we want to try to use what we've learned about increasing, decreasing, concave up, concave down intervals. And we want to remind ourselves that there are 4 different combinations of these things. So I could have a graph that looks like this, a graph that looks like this, a graph that looks like this, or this. So let's remind ourselves of what combination we've got here. This is increasing and concave down. This is decreasing and concave down. This is decreasing, concave up, and finally increasing and concave up. And so we're going to note these characteristics of our graphs, of our functions, above the graph, above the coordinate system that we're going to be using for graphing. And that's going to hopefully help me draw a nice picture and a pretty solid picture of what we got. So, and I guess one thing I should have mentioned up here, also, we should plot inflection points. That will help us as well. So let's get to this and do a couple of examples in this video. We're going to be using the same functions that we looked at back in sections 4.3 and 4.4, where we were finding increasing, decreasing, concave up, concave down, all that good stuff for these functions. And so our first one is y equals 6x cubed plus 18x squared. So you can see here below, I've summarized all the information that we gathered in our previous videos from 4.3 and 4.4. But let's go ahead and think about the other stuff that we were talking about. In terms of a domain, this is a polynomial. So our domain is all real numbers. And so there's no possibility of vertical asymptotes. So I don't have to worry about that. In terms of intercepts, well, y of 0 is equal to 0. So the origin is my y-intercept. And for x-coordinates, I want to solve. So this is for the y-intercept. And down here for the x-intercept, I want to solve 6x cubed plus 18x squared equals 0. Well, I can factor out 6x squared from both terms. And so I wind up getting 0 and negative 3. So those are going to be the x-coordinates of my x-intercepts. And then limits at infinity, both positive and negative. The limit as x goes to positive infinity of 6x cubed plus 18x squared. Well, remember that we focus on the term with the largest exponent. That's this one right here. As x gets really big and positive, I get 6 times a big positive number. So this is going to be going towards 6 times a big positive number. And so we would say this is going toward plus infinity. But as we go toward minus infinity, again, focusing on the leading term with the highest exponent, this is going to be going towards 6 times a big negative number. And so that's going to be going toward minus infinity as we go off to the left. So now let me show you how I'm going to encode the information that we've gathered already from our previous videos. We remember that this function was increasing everywhere except between -2 and 0. It was concave up to the right of 1, concave down to the left of 1, and I've got some, I know what my local max and local min values are. And so let me show you what I want to do with encoding this information, the increasing, decreasing information up here. So if I want to work with that, so I know that, so I'm going to draw 2 axes here, or I'm going to draw 2 lines. And in the lower one, so this, I have 2 spaces to work with now just above my graph. In the lower one, I'm going to include the increasing, decreasing information. And so I know that there were changes. Sorry about that. I know that there were changes at -2 and 0. So notice how I've got this scaling done on my axes down here. I'm using 2 units horizontally for each number that I've got. And because I know what my values are of y-coordinates, at least for my maxes and mins, I'm scaling things so that a single unit is worth, a single grid line tick mark is worth 3 units. So here I know that I'm increasing to the left of 2 and to the right of 0, and I'm decreasing in between. So this is how I'm going to take this information here and move it down above my graph. And then for my concave up, concave down, I know that there's a dividing line at -1. Over here, it's concave down. Over here, it's concave up. So now let me plot the points that I know something about. I know that I've got intercepts at 0, 0 and at negative 3, 0. So I've got an intercept right here and an intercept right here. I had a maximum at negative 2, 24. And I've got a minimum right here, and then my inflection point was at negative 112. So this is an inflection point. This is a local max. This is a, let me not put that right there. This is a local min. So let's try to connect these dots that I've drawn. So I'm starting off over here. My first piece is to look at this combination of increasing and concave down. And so I'm going to have something that looks like that. Next, I move to decreasing and concave down, and that goes until I get to, sorry, that's going to go till I get to here. So I've got decreasing and concave down. Now, between negative 1 and 0, I'm decreasing and concave up. So I can do that. And then finally, beyond 0, I'm increasing and concave up. So I do something like this. And then I remember that as x goes to positive infinity, my graph should keep going up and up. As x goes to minus infinity, my graph should keep going down, down, down. And so this is a reasonably carefully drawn graph that labels the important points of this function. I'm going to do one more before we stop this video. Y equals 2x e to the negative 1/4 x. So let's remind ourselves of some things about that. You can see what we've done, summarizing the increasing, decreasing, local max, concave up, concave down stuff. So in terms of domain, all real numbers again. Exponential functions are defined everywhere, so there's no problem, no possible vertical asymptotes. In terms of intercepts, y of 0 is going to be 2 times 0 times e to the 0, but that's going to be 0. So again, this graph is going to go through the origin. And then for x-intercepts, if I set this equal to 0, well, again, I know that this is never 0. And so I'm led to see that my only intercept is the origin. It's the only place it's going to touch any axis. Limits at infinity require a little bit of care. In this case, we're going to be using L'Hopital's rule because this is going to be an infinity times 0 form. X is getting really big, but with this negative exponent right here, e to the minus 1/4 x is getting really small. So remember what we do with an infinity times 0 form. I'm going to write this as 2x over e to the 1/4 x. I take the reciprocal of one of the functions, so I can get, in this case, an infinity over infinity form. So by L'Hopital's rule, I take the derivative of the numerator, derivative of the denominator, and now this is going toward 2 over a very big number. And so I get 0. So y equals 0 is a horizontal asymptote. If I want to take the limit as x goes to minus infinity, though, I get something entirely different. This time, this is getting really big, and this is getting big as well. Now let's think about that. If I'm putting a negative number in for x, then negative 1/4 of a big negative number is a big positive number, and e to a big positive number is getting really big. And so we would say that it's going toward, so I've got a big negative number times a big positive number, and so this limit is going to be minus infinity. So let me draw my axes here, or my lines above my graph. Not too much to fill in this time. So I've got something here, I've got a change at 4. And on one side, it's increasing, and on the other side, it's decreasing. And then my other change is way out here at 8, where I go from concave down to concave up. And so let me plot my points of interest. I said my only intercept was here at the origin. I've got a max when x is equal to 4, and the y-coordinate is about 2.94, so it's just a little under 3. So this is a local max. And my local min, or my inflection point, I'm sorry, is at 8, and the number just is a little bit above 2. Right here. So now let me try to draw this in. I start off increasing and concave down again. And so I'm going to be doing something like this. I go to decreasing and concave down until I get to right there. And then from then on, I'm decreasing and concave up. But I want to remember, let me draw this in. This is a horizontal asymptote out here. And so what's going to happen is I'm now concave up, but I'm going to be going off and getting closer and closer to the horizontal axis there. And on this side, I'm going off toward minus infinity. And so this is a decently careful graph of this function.